All right, welcome to Intro to Quadratic Functions. Okay, sorry, I had to get the screen right. All right, so quadratic functions, as we know from factoring, is when you have ax squared plus bx plus c. Of course, those could be plus or minus. Now what we're looking at is what happens when we put a y equals there. So we're going to be doing a bunch of stuff with quadratic functions. We're going to graph them. We're going to compare them to linear functions. We're going to look at where their solutions are, how many they have, what type they have. And then after that, there's several different ways to solve quadratic functions. So you can solve by graphing or solve by square roots or factoring, which we just did all last week. And then also quadratic formula. So today we're just going to take a look at how to identify quadratic functions. Okay, so you should have this in your notes. Now, from a graph, let's just look. So this is only just comparing linear and quadratic. So a linear function, of course, would look like this, right? This is a straight line. Quadratic function, I feel like if I asked you, what does a quadratic function look like? I would probably have several of you raise your hand and say, it's like a parabola, or you forget the word parabola and say, it's a U shape. So there we go. That's a quadratic function. So from a graph, it's super easy. Does it look like a line or does it look like a U? So it's a U, it's a parabola. All right, from a table, remember that when we took a look at linear functions, we looked at common differences. So remember, you have to look first at your x's, make sure they're going up by the same thing every time. They are. They're going up by 1. And then you take a look at how do I get from -5 to -3? Well, I add 2. -3 to -1, I also add 2. -1 to 1, I add 2. And so on. I add 2, and I add 2, and I add 2, and I add 2. So if the change in x is the same and the change in y is the same, then this is a linear function. So we call this, remember, a common first difference. First meaning like the first time I did it, the number was 2 all the way down. So is there a common difference? Yes, there is. Okay, moving on to the table of a quadratic function. Again, first look at your x's, and they're going up by the same thing every time, so they're all +1. That's great. Well, now we look at the y's. How do I get from 9 to 4? Well, subtract 5. 4 to 1, that's 3. So immediately I should tell this is not a linear function because there's no common difference. 1 to 0, -1. 0 to 1, +1. 1 to 4, +3. 4 to 9, +5. So is there a common difference? This question right here, well, no, there's not. But wait, there's more. So my little infomercial here. Now, if I take a look at the second difference, meaning how do I get from -5 to -3? Well, I add 2. And then -3 to -1, I add 2. -1 to 1, I add 2. 1 to 3, I add 2. 3 to 5, I add 2. So now is there a common difference? Of course there is. But it's a common second difference. And for those of you trying to see a weird pattern here, I know that like these are 2 and these are 2, but it's not always 2. That just happens to be. So that's the way from a table that you would look and see that it's quadratic. There's also some things you can do to look at like the symmetry, like I have 2 9s, I have 2 4s, I have 2 1s, and I have a turning point at 0. But that's a little, it's not always super duper accurate because sometimes you'll have that, but it'll be like an absolute value function instead of a quadratic. So you gotta be careful with that. So I would look for the common second difference. All right, so that's the table. Now from an equation. Well, I have 2x plus 3y equals 6. So this is remember we did this almost this exact same thing before when we were looking for linear functions. We said, well, can they be written in y equals mx plus b, or which is slope-intercept form, or ax plus by equals c, which is standard form. Well, now I'm looking for, there's a few different things. So your standard form, ax squared plus bx plus c, the standard form of a quadratic. We also have something called vertex form, which we don't really look a ton at in this class, but there is certainly, that is a format that you will see maybe in Algebra 2 more than right now. So basically, we're just going to look at each of these in turn and say, well, are they quadratic? Well, to be quadratic, you need a squared term. I mean, not just a squared term, right? Because if you have a cubed term too, like that's also not quadratic. So it needs, remember this term, you need a degree of 2, meaning that the highest exponent is 2. Okay, so let's take a look. So this one right here, number 1, 2x plus 3y equals 6. Does it have a squared term? No, it is not quadratic. It's actually written in standard form of a linear function, so that's linear. Moving on to number 2, I have y equals 4 times x minus 1 squared minus 8. Well, guess what? I have a degree of 2 right here. It's also in this crazy vertex form that I just told you about, but I don't expect you to recognize that. I expect you to see there's an x. It is raised to the second power. So this is quadratic. Now, if I take a look at number 3, y equals negative 3 plus 7x squared. What's my degree? It's 2. So yes, this is a quadratic function. I like that I just asked you a question, and honestly, I'm doing this to an empty room right now, and so nobody's here to answer me. But in my head, you answered me. I'm also looking out at the room right now, which is really bizarre, because I hope nobody walks by my classroom right now, because they'll think I'm crazy. Anyway, number 4. So y equals 4x squared minus 3x plus 11. Oh my gosh, ax squared plus bx plus c. Perfect. That is standard form of quadratic. So yes, it's quadratic. Number 5, y equals 3x plus 2. That's mx plus b. So no, that is not quadratic. That is linear. And then in this one right here, number 6, y plus 2 equals negative 7x. If I just move that 2 over, then this is y equals negative 7x minus 2. So no, that is also a linear function because it's also an mx plus b. All right, so just that's recognizing quadratic. So to review, from a graph, look for a parabola. And by the way, it could be like an upside down one, like a frowny face, a sad parabola, or a happy parabola. It can't be a weird parabola like this because that's just not a function at all. And then from a table, look for your common second difference. And then, and then from an equation, you look for a degree of 2. Okay. Now we are going to, the other thing we're going to take a brief look at today is what solutions are to quadratic functions. And if you paid like super strict attention, last week when we were talking about factoring, I brought this up as, how like when you factor and you get, x plus 2 times x minus 4, how really those are solutions, and negative 2 and 4, and it's where it goes through the x-axis. And right now, I know you're thinking, I have no idea what you're talking about. I don't remember that. That's okay. So here's the deal. A solution, this is incredibly important to know, a solution to a quadratic function are the points in which it crosses the x-axis. The x-axis. The x-axis. Okay. So you have 3 possibilities for numbers of solutions. So when you're looking at quadratic functions, you can either have no real solutions, and I say real because like that's legit. You can have imaginary ones, and you're like, imaginary stuff shouldn't exist in math. And I say, I know, but it does. But it is, don't worry about it right now. That's an Algebra 2 thing. You could also have one real solution, or you could have 2 real solutions. So meaning like If you have no real solutions, it never crosses the x-axis. If you have one real solution, it crosses once or hits it once. It doesn't really cross, it just kind of lands there. And then or you could have it cross the x-axis at two different places. So just so, to add to the confusion, solutions in algebra to quadratic functions are also sometimes called roots. Oh, my board is off, sorry. Or zeros. Or just simply x-intercepts. So those are all like the same as solutions. So if you hear me mention either of those, I'll probably say zeros more than anything else, but if you hear me say that, that's all the same thing. Okay, so just taking a look at each of these graphs, I want to know in graph A, what's the number of real solutions? Where it hits the x-axis once, there's one real solution. In B, what are my solutions? Well, it hits or crosses the x-axis here and here. There are two of them. In graph C, it never crosses the x-axis, right? It doesn't ever get down to there. So it has no real solution. All right. So what are the solutions of these quadratic functions? So first of all, each of them, what you should see is each of them has two. Second thing you should see is that this is an old school calculator. But you go through, if we're just assuming, which is fine, that this goes from this is 0 and that's 10, that's negative 10. So it went over, let me write this so you can see a little bit better. From the origin, you go over to negative 1. That's the solution. And then 1, 2, 3 is your other solution. So your solutions are negative 1, x equals negative 1, and x equals 2. And again, when you solve these, you solve them by graphing, or this is solving by graphing, which we'll get into in a couple of days, but it's literally just graph it and look and see where it crosses. Or you solve by square roots or factoring or quadratic formula. So, but this is just taking a look at what are solutions. So in this one right here, if you start from the origin, you have a solution at negative 1, and then 2, 3, 4, 5, 6, 7, 8. So negative 1 and negative 8. And you can write negative 8, negative 1. It doesn't really matter. But again, it's just where it crosses. So I want you to, I'll do it with you. I'll be all fancy and hold my calculator. I'll just have to tell some jokes while I do it because it takes forever in a day, as you know. So you have these three functions, and I want you to tell me, oh my gosh, this is taking forever. I want you to tell me first how many solutions it has, and second, where they are. Okay? So, All right. Clear that y equals. Hopefully they gave you time to go get your calculator anyway. Clear everything out of there. The first one was x squared. Was it minus 6x plus 9? Oh, for crying out loud. Let's see. Minus 6x plus 9. Okay, so x squared minus 6x plus 9. Okay. You know what? Don't graph it. Zoom 6. And then that way you know for sure your window is where it should be. Okay. So let's see. If I'm looking at this, I have one solution. And it is at 1, 2, 3. So it's at positive 3. It actually equals 3. So I would out of there. Oh, don't. Oh, no, I knew that was going to happen. Shoot. Okay, so it has two solutions. No, just kidding, one solution. And it is at x equals 3. I'm so bummed out because I accidentally closed out my calculator, so now it's going to take forever and a day for that to come back up. So, yeah. Anybody heard any good jokes lately? I have not. I would tell you some, but I don't have any. Okay, good. Whew. Saved by the calculator. So go back to y equals, clear it out, and I had x squared plus 4. X squared plus 4. Now hit graph. And if you take a look at it, Like, here's your x-axis. Does this cross the x-axis? That's a big fat no. So this has no real solutions. And then you can't say anything about like where the solution is because that's the big fat. I'll do that. Because there are none. So this one has no solutions. And what are the solutions? Well, that's not applicable because it doesn't have any. All right, last one is x squared minus 3x minus 10. So again, y equals in clear x squared minus 3x minus, oh, wow, what on earth? Hold on. 3x, there we go, minus 10. I don't know what I just did there. Hit graph. All right, so you don't see this whole graph. Like it kind of goes like that, but like all graphs have a turning point, so that doesn't really matter. Again, what matters is our solution. So where it crosses the x-axis is there and there. Oh, my board. All right, so this is at -2 and 1, 2, 3, 4, 5. Okay. So I have two solutions, and it's at x equals -2 and x equals 5. And what I would like love for you to see here, maybe you do, maybe you don't, and that's okay, is if you're to take a look at this, so like, forget that that's there for a second, that y equals. If I just said factor that, you would see what multiplies to -10 and adds to -3. And so, right, you have like your, well, if this is, 10 is negative, then you know 1 is plus, 1 is minus. And so if b is negative, then your larger factor is negative. So I have 1 times 10 or 2 times 5. So it's either -10 or -5. So 1 and -10 will give you -9. That doesn't work. 2 and -5 gives you -3. And then, so it's x minus 5 times x plus 2. Like these are the same numbers except opposite. And there's a reason for that, and I'll get there sometime next week. But I just wanted you to see that like sign-wise it's opposite, but numbers-wise that's the same. So this, I just kind of showed you solving by factoring real quick, just without explaining the rest of it. Okay, I think that's it. So here you go. Identifying quadratics and solving them. Not solving, finding solutions. Sorry. All right, that is it. I hope you enjoyed this lesson. You have your homework assignment, which I can't remember what it is right this second, but